I'm going to talk about nanoscience, resonant energy, and sensors. So we'll start with, let's see. So this is the outline. We'll talk about some work that I did with Sushanta Mitra, so I thought it's appropriate to start with that at Alberta. Then get into our new stuff, that triboelectricity, and then talk about the single wire power transfer, sensors, and talk about the little future ideas. So here is a video. Actually, if you take a platinum powder, let me see. So platinum nanoparticle, put it in a glass wool, and then put a little bit of methanol at the bottom. What you see is that this nanoparticles will start burning. It reaches a red hot, as you can see that. So what happens is that platinum catalytically convert the methanol into carbon dioxide and water. So this was found by Jerry Hu, who was a student of mine in Oak Ridge National Lab. So we thought maybe what we can do is to use this for energy conversion, converting methanol, for example, or ethanol or methane into heat, and using a thermoelectric element, then we should be able to get some kind of a power out of this thing. So we get the thermoelectric device, put the platinum nanoparticles on it, and you start heating it up. And what you see is that the power goes down. You can create around more than 100 millivolt. Even we go to even 1 volt in later. But you can see that it lasts only a few minutes, then it basically goes away. So we didn't know why this phenomenon is happening. So we started looking at the adhesion measurement with the AFM. These are nanoparticles. We can look at the heat in like this one, scanning thermal microscope, and we can see that they get very hot particles. But how come we cannot get any power out of this thing? So what we realized is that basically there are a couple of different ways heat is being generated and then transmitted across by conduction, convection, and radiation. And these are the nanoparticles on a glass wool. And basically what happens is that when methanol is reduced, it produces water, and water condenses right around this tip, the nanoparticle. Just like in an atomic force microscope, you see the capillary condensation. And basically, eventually it cover up the whole thing, and then platinum is no more accessible to methanol vapor. So basically it kills it. So the idea, actually it came also from Sushanta, if we can manage the thermal transport across the nanoparticle into the thermoelectric, so you have to maintain a credible temperature above 100 degrees or so, so water wouldn't condense and the methanol will be exposed to the nanoparticle. At the same time, you don't want to heat it too much, because you want the heat to come down to the bottom, to the thermoelectric device. And we were able to do that, and we can actually see the nanoparticle basically burning, is controlling the methanol methanol air ratio. You can make it red hot, and you can get loads of power. You can get more than 1 volt and sustain for a long period of time. We haven't published this work yet, but this is excellent work. So we can actually convert biofuels like methanol into heat and electricity. If we have a better thermoelectric coefficient, maybe we'll be able to get even more power out of this thing. So another area I want to talk about is a recent one, that is triboelectricity. You know ZL Wang at Georgia Tech. So we thought maybe we should give him some competition. But it's very hard to compete with ZL Wang, because ZL Wang published 1,000 papers in this area, hundreds of patents on it. But we found an Achilles heel for ZL Wang that he can create lots of potential but no current, right? Very little current. So I told my grad student, maybe what we have to do is to increase the current, not the potential. So I have a student from China, Shanghai actually. He decided to take up this challenge. I had another student from IIT. He didn't want to take up the challenge. He thought ZL Wang is a god and cannot challenge. So, so here is the triboelectricity works. You take two material, you rub it together, and there's a static charge develop, and lots, just like you walking on the carpet and get a shock during the winter time. And ZL Wang made a big institute in China actually. He's doing very well. He's a close friend of mine, but we compete too. So this is what his approach. He can create lots of power. So this is what we came up with. So we took molybdenum disulfide, make a PLD, pulse laser deposition, on the surface of a material like a silver grown on silicon. And basically, if you rub it with the AFM tip, and it creates lots of current. So there's lots of interesting physics here. So what ZL Wang and the triboelectric people are doing, they are using not a conductor here, they are using a polymer. So polymers, you cannot get the electrons out of them. But if you can move the electrons back and forth, you should be able to get lots of current. So this is what the topography looks like. This is our simple PLD and the conducting AFM, and you basically run it back and forth, and you get a huge amount of current. So this paper is actually accepted in Nanotechnology. It took a while. Referees gave us lots of hard time. They couldn't find anything wrong with the science, but only cosmetic things. So finally, it will come out maybe next week or so. So we have to have a Schottky on the top, on the molybdenum sulfide, and ohmic at the bottom. So that is the trick. So depending upon how you deposit the material, and you can get a good Schottky or a kind of not so good Schottky. And if you get a good Schottky, then you can create a depletion layer, and you can have an electron basically tunnel through the whole area. So we did a finite element modeling on this thing, and we kind of realized that there's a huge amount of field generated at the end, just because of the contact potential difference. It's only a few hundred millivolt difference, but it's a huge field, and that is enough to create the depletion layer in the molybdenum disulfide and pull the electrons go through it like a ballistically. So this is again little movie. This is Junlu trying to do he's rubbing it, and then you can see that it creates lots of the current actually, and it's actually measured it as a potential across a capacitor actually. And you can see that it works very well. So this paper will come out next week, and you should be able to see it in Nature Nanotechnology. So now coming to the next question. So we have two different ideas now how to convert the convert the energy into electricity. But how do you transmit it? I wouldn't talk about the storage at this time because we don't have time. So we went back to Tesla's old concept. Nikola Tesla. Tesla actually used to live in Buffalo, I was told that. So he had an idea that you don't need two wires for electricity transmission, just like what they teach you in physics, that you have to have the electrons need to go to the load, and then they have to come back home, right? And then they make a circuit. Actually, you don't need it. You can make the device in such a way that the load will be inside the circuit itself. It doesn't have to be outside. It's a kind of a little bit different way of thinking about physics. I'm a physicist by myself, so everything is consistent with the Maxwell's equations and so on. There's nothing wrong with this idea. So what we are doing, basically take a wire and create a standing wave, so the electricity or electric field get reflected from the tip of this wire back forming a quarter wave standing wave. Now, if we can get the potential difference from here to here, this is the node and this is the anti-node, and if we connect the load, it should work. But you may think that this is absolutely crazy, this shouldn't work, this guy should be put it in some lunatic asylum, because it doesn't make any sense. You're shorting your device, you're taking the light bulb and shorting the wire on it, and it shouldn't work. Basic physics says that it shouldn't work, but if you think about it a little bit more, say that it should work. Okay, so this is the wire. So we basically, you cannot do it with the 60 hertz frequency, because you will be thousands of meters long, or a couple of many thousands of miles long standing wave. But if you can increase the frequency to say 10 megahertz, then lambda is not that high. It's 10 meters or so. You can do a little calculation. And here is a standing wave, copper wire, actually put it on a wood and then connected to a light bulb. It's all sitting on a basically, the plastic bucket or something like that. So it works. Oh, this is that movie Amit was trying to say. So here is again, a 50-watt light bulb, aluminum foil, and this is the single wire. So there's a power supply underneath it, and you can just connect it. Okay, and he's touching it. So just put it there. It comes on, right? There is nothing going back. There is no return, no earth. Generally, people think that, oh, I have some kind of earth return. There is no earth return here. And you can touch it, and it is perfectly fine. This is because this is a piece of wood. And aluminum foil is to show that it's only single contact and single wire. So how does it work? Basically, this is that light bulb, 50-watt light. Here is 25-watt load. Basically, there's a coil that's the length of the quarter wave. And basically, you have to split it somewhere so that the load is in parallel to part of this coil. So all the physics of the circuit is perfectly fine here. And then maybe through the stray capacitance, we assume that it is completing the circuit. So this is another example. Again, this is you can buy this in Walmart for a couple of dollars and remove all the batteries, connect the leg to wires, and again this aluminum foil. So as long as it's sitting on the aluminum foil, it gets the power through the leg. It's all scotch tape it to the ground, to the legs, and it walks around. As long as they are on the aluminum foil, you will get the power, and if it walks off and is dead, there is no more power, right? But here there are some capacitors, they have some residual charges, so they can work maybe a couple of minutes more, and then it will drain completely, but it will find its way back again. So there's another one. You can have multiple ones. You don't have to use one. You can have hundreds of these things. And they are all resonantly coupled together. So they can even talk to each other. And we can also talk to them by superimposing signals onto this mylar, basically, aluminized mylar. And it's all one wire, right? So this is exactly what Nikola Tesla wanted to do a long time ago. And he wanted to power the whole world. The world will look like this aluminum foil. And so we also did that. So we wanted to drill a big hole in Edmonton. But unfortunately, Edmonton is always under snow, and we couldn't do that work. So we found a cliff, and we did that experiment. And we published paper. I wouldn't show that results here. So people said, oh, this is all interesting, little thing. Can you do real power? And I said, what is a real power? A scooter. So we went and bought a scooter in Amazon, $500, you can buy this scooter, and try to do it in the aluminum foil in the lab and make it run. So let's say, this. So my student said, okay, well, let's do it. So this is a video again, aluminum foil in the lab. And so there's nothing much to it. So this is the scooter, and it's above, couple of inches above the aluminum foil, so it's not even touching each other, right? And so now it is going to get charged. You can see that it is around 1.8 amperes. It's pulling through that contact, through the air actually. And it's perfectly safe, people. So it will run now. There it goes. So people said, okay, that's all interesting. So a big deal. You're doing it only in the lab. Can you do it outside? Okay, then we have to go and do it outside, right? People always raise the bar a little bit more. So here is a couple of my people. So they said, okay, we'll take it outside. This is again in Edmonton. Then we drove it on the outside. This is powered through this aluminum foil. But we didn't have enough aluminum foil to hold over Edmonton, but only part of the place we were able to show it. So like Amit said, now actually we can use, we don't need aluminum foil. We are good aluminum foil. Our body, it can actually support standing waves, right? So if you wear a watch contained batteries with all the circuit and we convert it into say 10 megahertz, your whole body will be energized. But you won't get electrocuted, believe me, because your current and voltages are out of phase. Say, power is V dot I, right? So VI cos theta. And when they are 90 degree off, there is no power. There is no real power unless it comes into the load. So that is a trick here. So that's why you can touch it, you can walk around on it, and nothing will happen to you. Now your body is energized, and you can have implanted sensors and things like that in your body. And you don't need a pacemaker with a battery in it. The pacemaker itself is very tiny. The battery is the biggest problem. So I couldn't find any volunteers, so my postdoc actually volunteered. So he's connecting the power to his hand, and the power comes on his other hand or on his head. He's smiling, so he's not under stress or any kind of problem. You see, or other hand, or anywhere you want, you can actually power the whole body. So now I'll go into sensors a little bit and then try to finish it up as soon as possible. I basically do a cantilever, like in the AFM. I use it as a sensor, so you can do all kinds of interesting things with it. So these are some of the devices we made long time ago. This again, around 32 different cantilevers in a microfluidic channel, all piezoresistive devices, and all this from, some of them are when I was at Oak Ridge. And this is a little implantable sensor. There are 8 cantilever underneath this titanium frit, and you can implant in the body. And we did this in the rat with Tom Farrell at University of Tennessee. So all the electronics are right here. It's all, you can buy it from the store, digital electronics, and there is a, what you call the 8-channel telemetry. So information is coming from all the 8 channels at the same time. So I don't have the picture for the image for the rat where we implanted and looked at the blood gases. This is one example of a cantilever. You can make it into a hydrogen sensor. Just put a palladium on the cantilever, and the cantilever will bend with respect to the hydrogen concentration. And we found some very interesting idea, actually. It also came out in scientific report. If you put a nano tube or nano pillars or nano rods on the surface of the cantilever or a resonating structure, and provided these nano rods are the distance between them equal to the mean free path, which is around 60-70 nanometers in air, immediately the Stokes law is no more valid. It's interesting. Stokes never said it is valid at nanoscale. It actually, it can do amazing things if you go to nanoscale devices and basically modify the surface with the nanostructures, and equal to distance between them should be around mean-free path. And then very interesting effect. So we started using that, basically looking at the viscosity. Nobody uses viscosity for sensing because it's a useless parameter practically, unless you are using oil sands or bitumen or something like that. But most of the time, viscosity doesn't, it's not a good indicator for materials. But if you can enhance the dynamic range of the viscosity at a given temperature, and that's what we are doing here with the nanostructures, then viscosity itself or dissipation itself can be a good sensing parameter. So we also did another one. We can modify the cantilever, make them bimetallic, and so we don't have to look at the Beer-Lambert's law. Basically, that's what most of the time FTIR and ATR and things like that use. Basically, you have to count the photons. In our case, we don't want to count the photons, but we want to look at the dissipated heat. And so when you shine light on a material, the material absorbs the light, then it gets hot, and then bimetallic cantilever will bend. And here is a mercury light from a mercury arc lamp light from using a monochromator, and you can see the cantilever bending as a function of wavelength. You see how beautiful it is, the spectrums, mechanically seeing it. So we thought we will put some naphtha on a bimetallic cantilever. So it's a picogram amount of naphtha adsorbed on the cantilever, and you are shining infrared 2 to 14 micron, and you can see all the peaks, molecular vibration as identified here. And this is the ATR, and this is the grazing angle FTIR. And you need a milligram amount of material here, you need a picogram amount of material, is a cantilever based upon known Beer-Lambert's principle, basically non-radiative decay. This is counting photons. And look at this, the signals are amazingly good actually. So people said, okay, vapor is fine, what about liquid? So we made a cantilever and then formed a little microfluidic channel on the top of it. And so this is the channel, so you can fill it with the liquid. Scott Manalis at MIT started this thing, so we borrowed it from him. And then now we can get spectrums of liquid in it. You can look at the density, viscosity, chemical composition by spectroscopy, and thermal properties. This is a amphisilin salt, 50 picoliters inside the cantilever, and this is the spectrum. This is a mechanical bending of the cantilever. So this is where I'm going to stop because we are going to run out of time. So the nanomechanical sensors, we can combine it with the nanoscience and the electrical power. And where we can use this is these smart cars and roads and the Internet of Things and all those interesting things we can do at this time. I'll stop here. I'll be happy to answer any questions that you may have. So you have a bimetallic cantilever which is extremely sensitive to temperature, like a thermostat at home, and you can get a sensitivity around 3 millikelvin very easily. That's a background, you can say. Now you have adsorbed the molecules on the surface. Most of the time silicon nitride and gold, that are the bimetallic components, they don't absorb this light. So if you put a naphtha, and if you put the infrared radiation in the mid-infrared, which is mostly free of overtones. So the molecules start vibrating, and when you vibrate, your excited state and you decay, come to non-excited states by phonons, right? You create phonons in the material. It's a little bit more complicated, but then, so there's a little heat generated, and that heat is enough to make the cantilever bend. So when you move the wavelength away from that absorption frequency, it comes back. So what you are seeing when you sweep the wavelength of the infrared, you are exciting the molecule at certain time, and at other times you are not. So the cantilever will move up and down depending upon the number of molecules get excited.
You get more like both information how much in.
Yeah, you can get you look at the peak height, it will tell you how much. and then the location of where it is absorbing you the energy of that.
Spectroscopy.
Yeah, the bond energy, basically, the vibration frequency. Yeah, thanks.